See, now we have the equations. Shall we plot and see? Because it will give a better idea.
That is true.
Like the diode.
Correct. Correct. So let's do it. So let's take the PNP transistor. So
PNP or NPN?
we'll take the NPN. Sorry.
Yeah.
Because that's what we have been seeing.
Correct.
No?
Correct.
So NPN.
Yeah.
Base, collector,
Emitter.
emitter. Correct. The NPN BJT.
Yeah.
Okay. Well, we saw that these are the three equations we know, no? IC is beta times IB.
Yeah.
Then IC is alpha times IE.
Yeah.
And we said that IC plus IB is
IE.
IE. These are the three equations we know.
Correct.
We also know that VBE is forward bias, so VBE on when it is on, right? So that we know.
Yeah.
Okay.
What will be typical value of beta?
We said alpha is very close to 1, no? So that means, and we also said beta is alpha by 1 minus alpha. If alpha is very close to 1, then beta should be very large. So probably like 100. If alpha is 0.99, no? Then beta will be 0.99, almost 1 by 0.01. So almost 100.
Okay.
Right? So typically we want in a really good NPN transistor, beta will be like 200, 300, 400, numbers like that. Definitely you want it to be as large as possible. Correct. Okay. Which means if your, let's say, emitter current or collector current is, let us say, in milliamperes, your base current should be in microamperes, right? So maybe 2 orders of magnitude smaller.
Okay.
So you wanted to plot, no?
Yeah.
We will start with the easy one. So we said that the base-emitter junction is forward biased.
Correct.
Shall we plot the current and voltage?
Yeah.
Okay. So I am going to plot IE versus VBE. We said that it is just a diode equation. No?
Correct.
This is very simple. We have done this before.
Yeah.
So maybe something like this.
Yeah.
Right?
Correct.
And this is VBE on.
Yeah.
Maybe 0.7 volts. Something like that. Right? For silicon.
In fact, it's a little bit exaggerated.
Exactly. I've exaggerated a lot. But yeah, something like this. Right? Okay, so this is easy.
Easy.
Very easy. So for any value of VBE, right, which is around 0.7. So let's say slightly higher than 0.7, the device can conduct a large range of currents.
Correct.
That's what we want to say. So in many cases, you may even say VBE is VBE on, which is 0.7.
Yeah.
Correct?
Yeah.
Okay. The minute you know emitter current, you can find out collector current.
That is true.
From is alpha times IE.
Yeah.
And then you can also find out base current.
True.
Right? 1 over beta times IC.
Oh.
So you can find out, looks like, everything about the device. Right?
From this itself.
From this itself. Well, almost everything.
Correct.
You must be missing something, no? If it was just this, no, it's just a diode.
Yeah.
Right? What is missing? Collector. This is only showing 2 terminals.
Correct.
We need to bring in the collector, no?
Collector base should be always reverse biased also.
Should be reverse biased also. In fact, that also may be easy, no? Shall we try plotting it?
Yeah.
Let's see what we can plot.
Yeah.
So, shall I plot here? So, we want to plot something else. We said base current is very small, no need to plot. So, we will plot again emitter current only. But we want to plot against base emitter. Collector base is reverse biased.
Yeah.
So, which means actually collector emitter will just be collector base plus 0.7.
Repeat again. Collector emitter.
Collector emitter
BCE.
voltage VCE will just be collector base plus VBE, which is 0.7.
True.
We will just plot against collector emitter voltage.
Okay.
So let's just do that.
Yeah.
That seems to be some standard way of plotting.
Yeah.
Okay.
So in that, VBE is not much changing.
Is not much changing, right? We can just assume that VBE is constant, we will get one curve, right?
Yeah.
So let us say we pick one point. Shall I plot it here? So let us say I take this point.
Yeah.
I get one VBE1 and IE1, right? I just call it like this. If I take for this particular IE1 VBE1 combination, I keep changing the collector voltage.
Yeah.
Correct? That's what we are saying. Then we will want a curve. It should not depend on collector emitter voltage at all, no?
Correct.
VBE is forward bias, base emitter junction.
Yeah.
Emitter current is flowing. Should not change.
Yeah.
Right? So maybe something like this.
It has to be like that.
It has to be like that.
Yeah.
But now, so this will be IE1.
For VBE1.
For VBE1. So I'll mark it as VBE. This is a curve for VBE1. Correct? It is not changing. If I chose some other point, no. So maybe I'll show it using this color. Suppose I chose this point. So IE2, I will get VBE2.
So this VBE1, VBE2 are minute.
Very small changes. This is exponential, no?
Correct.
Maybe instead of 0.7, I become 0.71, 0.705, something like that. So they're very, very small changes. But the emitter current change is a lot. Right? So everything is almost 0.7.
Almost same current goes through collector base.
That is
so
correct.
That's the point.
That is the point. Right. So if you do this, you will get one more curve, no?
Yeah.
So maybe I'll go back to my red color. I'll exaggerate it and maybe show it like this, right?
Yeah.
So this is VBE2. In fact, I'm just marking it as VBE1, VBE2. Actually, what matters is emitter current.
Correct.
Not all of these VBE1, VBE2, everything is going to be very close to 0.7.
Yeah.
That is what we are saying. And this is IE2. And so on. You can now plot. It looks like there is a whole range of curves, no? Something like this. You can plot, right?
So which means I can change VB using something at what I want, and then make large amount of change in current from collector to base.
From collector to
collector to emitter. Collector to emitter.
Correct.
So it's a voltage controlled.
Correct. It seems to be you are controlling the voltage across two junctions.
Correct.
But changing the current through the other terminal, collector current terminal, right? I am now relating it. I understand where you are going. It seems like you are changing the current through some third terminal.
Correct.
Using the voltage.
Correct.
Is this why it's called a transistor?
Maybe.
Maybe transistor is what we thought, no?
Maybe
it is because of that. Right? Okay. Okay. So now this is great. This is good, no? So VCE will be 0.7 plus VCB.
Yeah.
Right? So this is good. But if I keep reducing this, no, I have not completed the curve. Something should happen. Otherwise, we are just plotting flat curves.
So at some point, that junction will become forward biased.
Forward biased. And if the junction becomes forward biased, this device will not work properly.
Then,
First itself.
Then these equations are not valid.
These equations are not valid. Right?
Or not fully valid.
Not fully valid. So I'll just say. So when.
In the active region.
In the active region. Valid in the active region.
Yeah.
Which is this flat region. Correct? Now if you reduce VCE, at some point in time, the collector base junction will become forward biased.
Yes.
Right? At that point, it will no longer be like this.
Yeah.
We don't want to use it there also.
Yeah.
So we will just see. So it turns out that you will have a something like this. I will complete the curve. you'll get something like this, and so on. You'll get a whole bunch of curves like this, right? So you normally don't want to use it along this line, correct? You can only use it in the active region. So I'll maybe mark it like this. So so this region is the forward active region, correct? Maybe they're not able to see. I'll use a different color.
Yeah.
So I use this one.
Yeah.
This is the forward active region. And of course, the device characteristics will extend. We don't need to worry about it now. They might extend into the third quadrant, but you will never use it. This device is built only to work in the first quadrant. In fact, that is why this is called the forward active region, because current and voltages are positive with our convention.
Yes.
We know that we saw in the diode, no, third voltage becomes negative, current becomes negative. We don't want to go into that for this device.
And once we know this, it's only, once we know IE, IC is straight away known.
Straight away, no. Correct. You know exactly.
Alpha, yeah.
Alpha, beta, all of these things will relate this. In fact, now I also realize there is one more set of, you can create many equations like this. You can, since beta is alpha by 1 minus alpha, you can get alpha as beta by 1 plus beta, right? Yeah. So maybe we'll just write that down here. So this is also one useful equation to use.
Correct.
But we already said that. You can get a whole bunch of relationships. Correct. So we are now, I think we understand that we need to use the device always in the forward active region. So base emitter forward biased, collector base reverse biased, and emitter current is exponentially related to the base emitter voltage, correct? And beta is large, alpha is very close to 1. I think you put all of these together, you can now build circuits, no?
Yeah. So this is for NPN.
Correct.
What about PNP?
Shall we do the same thing quickly for the PNP? So, in the case of the PNP transistor, base, emitter, collector. I have just drawn it like this, upside down, because that's the conventional way. A lot of people like to draw it like that. The difference is that we saw emitter current now flows into the emitter, collector current flows out of the collector, and now base current now flows out of the base. So current directions are slightly different. Now the voltage directions also have to change, no? Because now we don't have a base emitter junction.
Emitter base.
Emitter base junction.
That has to be forward biased.
That has to be forward biased. So this is your emitter VEB. Has to be forward biased. So VEB will be 0.7. And now the base collector junction. So let's P. This will help us. So this is P and this is N. So PN has to be forward biased. And now base collector is a higher voltage. So this is reverse biased. So I'll draw it like this. Forward biased. This is reverse biased. So EB is about 0.7 volts, let us say. Right? And now you talk about emitter collector voltage, which will be VEB plus VBC. And VEB will be 0.7. So now we know this. All other relations stay the same.
Correct.
Right? Alpha, beta. We don't need to write it explicitly.
No need.
So all of these, IC is beta times IB, IC is alpha times, they all remain the same. The plots will change slightly.
Because the
polarity has changed.
Yeah.
So what I will do, I'm just going to make my job easier. I'm going to copy this and just change the polarities. Shall we do that?
Yeah.
That is easy because we don't need to keep redrawing. I'll move this down here. So emitter current entering depends on the emitter base voltage. correct? So now this is all VEB on.
VEB1 and 2.
So yeah, correct. So this will be VEB1. This is VEB. Same thing happens here.
Yeah.
But now this also needs to change.
Yeah.
Instead of VCE, you have VEC.
EC.
But the rest of the curve stays the same.
Yeah. So the
Very
behavior is the
straightforward.
same. Yeah.
Behavior is the same.
Yeah.
So in fact, you can clearly see that they are very similar, right? So if you know how to build something with an NPN, you can build something with a PNP and vice versa. Very nice.